Okay. Till now, in this chapter, we have discussed DFT, inverse DFT, some properties of DFT, circular convolution, and linear convolution using circular convolution. And only one topic left here, that is differences between linear and circular convolution. After the discussion of this topic, we can move on to FFT. Okay. First, linear convolution. And circular convolution. So the first one in linear convolution is see x of n is of length n1 and h of n is of length n2. Then y of n is equal to x of n convolved with h of n should have length n1 plus n2 minus 1. Similarly, in the case of circular convolution, here x of n should be of length n and h of n should also be of length n and y of n will also be of length n. If this is not the case, if these two signals are not of equal length, then zeros should be added or appended at the length of shortest at the end of shorter sequence. In order to make the length equal. And this technique is called zero padding technique. And this technique is called zero padding. Okay. Coming to the second difference, Here, input sequences need not to be periodic. Here, at least one of the input sequence should be periodic. And the next one is output is also periodic here. Here, output is also periodic with the same period as input. Okay. Here, if the length of output sequence is greater than the length of input. Here, length of the output sequence is equal to the length of input. Here, in fact, first and fourth point are one and same. Here, in the first point, we are mentioning that length of both the sequences should be equal and length of output sequence is also equal to the length of input sequence. Right? That's what we are mentioning here. Right? And the point is, if x of n is in the range of 0 to n1 and h of n is in the range of 0 to n2, then phi of n should be in the range of 0 to n1 plus n2. Whereas here, if x of n is in the range of 0 to n and h of n is in the range of 0 to n, then phi of n should also be in the range of 0 to n. If these are not, if one of the signal is not in the range of 0 to n, then that should be extended to n, right? Whichever might be the greater. And if x of n అనేది 0 to 10 only, h of n అనేది 0 to 3 only, we should extend h of n to 0 to 10 by adding some zeros at the end of the short sequence, right? And the last and final difference between linear convolution and circular convolution is linear convolution involves linear shifting and linear folding operations. And circular convolution involves circular shifting and circular folding operations. And here we have learned circular convolution using 4 different methods: table method, matrix method, circle method, using convolution property of FFT. Okay. And these are the 6 main differences between linear convolution and circular convolution. And of course, we can also say that the expansion of the convolution itself, x of n convolved with h of n is equal to sigma k is equal to minus infinite to plus infinite x of k into h of n minus k. X of n circularly convolved with h of n is equal to sigma m is equal to 0 to n minus 1 x of m into h of n minus m mod n. Right? So we can say that these 7 are the main differences between a circular convolution and linear convolution. Is it clear? మనం ప్రీవియస్లీ డిస్కస్ చేసిన అంటే ఈ టాపిక్స్ లో మీకు వీటిలో ఉన్న డౌట్ ఉంటే విల్ డిస్కస్ దెమ్ ఆఫ్టర్ దట్ విల్ మూవ్ ఆన్ టు ఎఫెక్టివ్ టాపిక్. ఇవి క్లియర్ ఉన్నాయా? మీ టాపిక్స్ అన్ని క్లియర్ ఉన్నాయా మీకు? ఏదైనా రిపీట్ చేయాలన్నా Okay, thanks for responding, and it seems to be clear. So we can move on to FFT topic. See, FFT కొంచెం like I can say కొంచెం lengthy అమ్మా, కాకపోతే చాలా సింపుల్ టాపిక్, చాలా అంటే చాలా సింపుల్ టాపిక్. ఓకే, FFT means fast Fourier transform. సి ఎఫ్ఎఫ్టీలో మనం కొత్తగా ఏ ఫార్ములాస్ నేర్చుకోమండి, అండ్ కొత్తగా ఏం కొత్తగా ఏం నేర్చుకోము. ఆల్రెడీ డిఎఫ్టీలో నేర్చుకున్న వాటిని సింపుల్ గా సాల్వ్ చేయడానికి ట్రై చేస్తాం. ఈవెన్ మనం డిఎఫ్టీలో మ్యాట్రిక్స్ మెథడ్ చేసేవాళ్ళం కదా, 4 పాయింట్ డిఎఫ్టీ అయితే 4/4 మ్యాట్రిక్స్ వస్తుంది, రైట్? 4/4 మ్యాట్రిక్స్ వస్తుంది. అదే if we want to find 8 point DFT, then we need to have 8/8 Quidel factor matrix. Then we need to have 8/8 Quidel factor matrix, which is highly difficult to compute by using matrix methods, right? So in order to compute larger DFTs or DFTs for larger values of n, we are choosing FFT algorithms. Okay, let us see the computational complexity of DFT initially, then we'll see how that computational complexity is reduced by using FFT algorithms. Okay, so let us consider if x of n has n point DFT of x of k, then x of k is evaluated as sigma n is equal to 0 to n minus 1 x1 of n into omega n power nk, where k is equal to 0, 1, so on, n minus 1. Okay, let us try to expand the summation initially. So x of k can be written as x of 0 plus omega n power, x of k can be expanded as x of 0 omega n power 0 plus x of 1 omega n power k plus x of 2 omega n power 2k plus so on plus x of n minus 1 into omega n power n minus 1 into k. And this is the valid expression for k is equal to 0 to n minus 1. Let us substitute k is equal to 0 to n minus 1 in this equation. Then it would be x of 0 omega n power 0 plus x of 1 omega n power 1 plus x of 2 omega n power 2 plus so on plus x of n minus 1 into omega n power n minus 1, right? X of 1, x of 0 omega n power 0 plus x of 1 omega n power 1. These are not zeros, right? Because in this equation, since k is equal to 0, then the entire table factor should be 0. X of 2 omega n power 2 plus so on plus x of n minus 1 into omega n power n minus 1. Similarly, at last, if we want to write the equation for x of n minus 1, then it would be x of 0 omega n power 0 plus x of 1 into omega n power n minus 1 plus x of 2 into omega n power 2 into n minus 1 plus so on plus x of n minus 1 into omega n power n minus 1 into n minus 1. So if you observe the single equation, in this single equation, every term is associated with a multiplier. Every term is associated with a multiplication, right? And there are n terms in this equation. So there are n number of multiplications associated with one equation, and there are n such equations, So n number of multiplications per equation and n equations. So n into n is equal to n square number of multiplications. So in order to solve an endpoint DFT, we require square number of multiplications. Right? So now let us try to find out the number of adders. Okay. Okay, if we want to add 4 numbers, how many adders are required? If we want to add 4 numbers, how many adders are required? Very good. 3 adders or 3 additions are required. Okay. And if you observe one equation, there are total n terms in one equation. There are in total n terms in one equation. So n terms ని యాడ్ చేయడానికి మనకి n minus 1 ఎడిషన్స్ అవసరం అవుతాయి. n terms ని యాడ్ చేయడానికి మనకి n minus 1 ఎడిషన్స్ అవసరం అవుతాయి. Because if we want to add 4 terms, we require 3 additions. So if we want to add n terms, we require n minus 1 additions. And there are n such equations to solve an endpoint DFT. So the total number of additions required are n into n minus 1. Total number of additions required are n into n minus 1. So for an endpoint DFT, total number of additions required is equal to n into n minus 1, and the total number of additions required is equal to n square, right? So by using this FFT algorithms, this number is drastically reduced. By using this FFT algorithm, this number is drastically reduced. So if you want to, these are the computational complexities for endpoint DFT. If you want to do the same for FFT, then the total number of complex additions required will be n log n to the base 2, and the total number of complex multiplications required is equal to n by 2 log n to the base 2. N log n to the base 2 and n by 2 log n to the base 2. Let us try to compare these parameters for different values of n initially. So let us consider n is equal to 4. Next, let me consider n is equal to 32. and n is equal to 128. Okay, so first multiplications. Let me find out multiplications, because implementation of adders is very easy compared to multipliers. Because in order to implement a 4-bit multiplier, in general, if you want to multiply two 4-bit numbers, then we usually accomplish it by using repeated addition process. So more number of adders are required for multiplication process compared to addition process. So when n is equal to 4, n square value is equal to 16, right? And n by 2 log n to the base 2 value is equal to, n by 2 means 8 log, see, 16 can be written as 2 to the power of 4 to 2, that is equal to 8 into 4, that is equal to, sorry. Here n value is 4, isn't it? Sorry. So n by 2 means 4 by 2 log 4 is equal to 2 square to the base 2, that is equal to 2 into, see this can be written as 2 into 2, that is equal to 4. So మనం డైరెక్ట్ గా DFT ఇంప్లిమెంట్ చేస్తే మనకి 16 నెంబర్ ఆఫ్ కాంప్లెక్స్ మల్టిప్లికేషన్స్ రిక్వైర్ అవుతాయమ్మా. అదే మనం FFT బై యూజింగ్ DFT by using FFT చేస్తే we require 4 number of multiplications, right, which is almost less than half. Okay, so if we consider 32, then n square value would be 1024, and n by 2 log into the base 2 value would be n log n. See here I'm considering multiplications, right? So we can consider it as n log n to the base 2 means 4 into 2, which would be 8. ఈ n by 2 log n to the base 2, n log n to the base 2 ఎలా వచ్చింది అని మీరు పెద్దగా కష్టపడక్కర్లేదమ్మా. Because we can easily find these are the results of FFT algorithms. L by 2 n log n to the base 2 and n by 2 log n to the base 2 అనేవి. These are the results of FFT algorithms. So మనం finally FFT algorithm prove చేసిన తర్వాత మనకు వచ్చే conclusions ఈ two values. Just DFT ని FFT ని కంపేర్ చేసి FFT is computationally efficient అని మీకు చెప్పడానికి I'm just mentioning that here. Okay, so by using FFT మనం ఏం చేస్తున్నాం, we are splitting an endpoint DFT into multiple n by 2 points. See, let us try to compute these values. Let us try to compute these values. This is 1024 and this would be 160. N by 2 log n to the base 2 value would be 160. And if n is 128, then n square will be 16,384 and it will be 896. So if you observe the computational complexity, that would be greatly reduced if we use an FFT algorithm instead of computing DFT directly. Okay, so here usually for an FFT algorithm we usually mention radix. Okay. Before going to radix, let us see how this FFT algorithms are reducing the computational complexity of DFT. Okay, here in our topic we are discussing radix 2 FFT algorithms. Okay, there are different radixes. We can choose radix 3 algorithms, radix 4 algorithms or radix n algorithms. కాకపోతే మిమ్మల్ని కన్ఫ్యూజ్ చేయడానికి ఎగ్జామ్ లో ఒక్కొక్కసారి స్టేట్ అండ్ ప్రూవ్ రాడిక్స్ MFFT algorithm అంటారు. మనం M అంటే డైరెక్ట్ హెడ్డింగ్ అయితే రాడిక్స్ MFFT algorithm అనే పెడతాము. ఫస్ట్ లైన్ వచ్చేసి లెట్ us consider m is equal to 2, because మన సిలబస్ లో ఉంది రాడిక్స్ 2 వరకునే, మాక్సిమం ఎంటెక్ రేంజ్ లో కూడా రాడిక్స్ 4 ఆల్గరిథమ్స్ వరకునే మనం డిస్కస్ చేస్తాం. Okay, so radix 2 FFT algorithms low, we should consider n value should be equal to 2 to the power of m. N value should be equal to 2 to the power of m, right? And initially in first stage of decomposition, this n point DFT is splitted into 2n by 2 point DFTs. And in next stage of decomposition, each n by 2 point DFT is decomposed into n by 4 point DFTs. And this decomposition continues until a length of 2 point DFT is achieved. Okay. So let me consider n is equal to 8. n is equal to 8 consider చేసుకుంటే n square value ఏమవుతుందండి? 8 square, that is equal to 64. మనం కనుక n is equal to 8 point DFT ని డైరెక్ట్ గా సాల్వ్ చేస్తే we require 64 number of multiplications, right? Let us see how this value is reduced by using FFT algorithm. So మనం decomposition start చేస్తే this 8 point DFT will result in 2 4 point DFTs. This 8 point DFTs will result in 2 4 point DFTs, right? n point DFT ని కంప్యూట్ చేయడానికి n స్క్వేర్ మల్టిప్లికేషన్స్ రిక్వైర్ అయితే n by 2 point DFT ని కంప్యూట్ చేయడానికి మనకి n by 2 whole square multiplications రిక్వైర్ అవుతాయి, right? So n by 2 whole square plus, and there are two such, n by 2 whole square plus n by 2 whole square, that is equal to 4 square plus 4 square, that is equal to 16 plus 16, which is equal to 30. So after first stage of decomposition, the number of multipliers required are reduced to 32 from 16, right? And as I said, this decomposition should continue until a length of 2 point DFT is achieved. So in further stage of decomposition, this n by 2 point DFT is reduced, is split to 2 n by 4 point DFTs. Yeah, tell me. Right? So if we have n is equal to 8, then the decomposition is of 3 stages. First stage 2 4 point DFTs, and in second stage 4 2 point DFTs. Since we are choosing radix 2 FFT algorithms, there won't be any further stage of decompositions, right? For an n point DFT, it requires n square multiplication. So for n by 4 point DFT, it should require n by 4 whole square number of multiplications. And there are 4 such blocks here, right? So 2 whole square into 4. 2 2s are 4, 4 4s are 16, right? So ఇక్కడ మనం ఏం చేస్తామంటే, ఇన్స్టెడ్ ఆఫ్ ఇంప్లిమెంటింగ్ DFT డైరెక్ట్లీ, we usually decompose చేయడం వల్ల 64 number of multiplications are reduced to 16. 64 number of multiplications are reduced to 16. That's it. Okay. And there are 2 FFT algorithms. One is DID-FFT or DIF-FFT. Decimation in time, FFT algorithm, and decimation in frequency. Clear? See, ఇప్పుడు ఇక్కడ మనం radix 2 డిస్కస్ చేసాం అనుకుంటున్నా. If suppose radix 3 algorithm కనుక డిస్కస్ చేయాలి అంటే n should be equal to 3 to the power of m, and in first stage of decomposition it is split into 3 point DFTs, And in next stage of decomposition, it would be further splitted into 6 point n by 6 మనకి radix ఎంత ఉంటే అన్ని parts అవుతుంది and DFT will be divided by that radix. Okay. See, నేను algorithm discuss చేయాలి అంటే నాకు complete గా 50 minutes టైం కావాలమ్మా. algorithm స్టార్ట్ చేస్తే డెఫినెట్ గా మినిమం 50 minutes పడుతుంది. Let us try to discuss the first part of this algorithm, DID FFT algorithm. Okay. In this DID FFT algorithm, if x of n has n point DFT of x of k, then x of k is equal to sigma n is equal to 0 to n minus 1 x of n into omega n power nk, where k is equal to 0, 1, so on n minus 1. Right? In first stage of decomposition, so in this first stage of decomposition, we want to split an n point DFT into 2n by 2 point DFTs. అట్లా స్ప్లిట్ చేయాలి అంటే మనకి ఏదో క్రైటీరియా కావాలి కదా, అదే we can do it in both ways. See, if there are 10 numbers like this, we want to split this 10 numbers into two equal set of numbers. అంటే 10k half అంటే 5 అవుతున్నాయి కదమ్మా. We can consider there are two logics to half this number. One is first half and second half. First half అంటే 1 to 5 and the second half వచ్చేసి 6 to 10. Otherwise, we can also split these numbers basis on even and odd values, right? We can consider all even numbers at a time and all odd numbers at a time. This is one and this should be the second. Right? So ఇక్కడ మనం DID FFT algorithm లో ఏంటంటే ఈవెన్ అండ్ ఆడ్ బేసిస్ కింద n ని n by 2 ని n by 4 లో స్ప్లిట్ చేస్తాము. DIF FFT algorithm లో అయితే ఫస్ట్ హాఫ్ సెకండ్ హాఫ్ అట్లా స్ప్లిట్ చేస్తాం. Okay. So in first stage of decomposition, we are going to consider the even indexed sequences and odd indexed sequences. ఇక్కడ మనకి 0 తో స్టార్ట్ అవుతుంది కాబట్టి we should split the sequences as, అంటే ఇప్పుడు suppose x of n has x of 0, x of 1, x of 2, x of 3 and so on, x of n minus 1, then even indexed sequence x of n consists of x of 0, x of 2, x of 4 and so on. The last one would be x of n minus 2. And odd indexed sequence should be x of 1, x of 3, x of 5 and so on, x of n minus 1. This is how we are going to split the actual x of n here. Is it clear? ఇక్కడ మనం ఒక n point DFT ని n by 2 point DFT కింద స్ప్లిట్ చేయాలి అంటే we need to split the input sequence. Input sequence ని స్ప్లిట్ చేసేటప్పుడు we may follow the even index odd index logic or first half second half logic. Even index odd index logic ఏమో DID FFT algorithm లో మనం చూస్ చేసుకుంటాం. ఫస్ట్ హాఫ్ సెకండ్ హాఫ్ కన్సిడరేషన్ ఏమో మనం DIF FFT algorithm లో కన్సిడర్ చేసుకుంటాం. Since we are discussing DID FFT algorithm here, let us consider the even index and odd index. Okay. So here Rx of k can be split into sigma n even x of n omega n power nk plus n odd x of n into omega n power nk. Okay. So when n is even, n is equal to 2r. When n is odd, n is equal to 2r plus 1. So total number అయితే ఇక్కడ sigma n is equal to 0 to n minus 1 అని డిస్కస్ చేశాం కదండి. హాఫ్ కాబట్టి 0 to n by 2 minus 1. Since the first one corresponds to even, this should be r. Even kabatti r is equal to 0 to n minus 1, n by 2 minus 1, x of 2r omega n by 2 power omega n power 2rk plus sigma r is equal to 0 to n by 2 minus 1, x of 2r plus 1 into omega n power 2r plus 1 into k, right? Total 0 to n minus 1 ఉన్న summation ని 2 parts కింద చేసాం కాబట్టి 0 to n by 2 minus 1, n by 2 minus 1, right? ఇక్కడ n is equal to even ఉన్నప్పుడు we have considered n is equal to 2r, and when n is equal to odd, then we have considered it as n is equal to 2r plus 1. Okay. In this case, k is equal to 0, 1, so on n minus 1, right? So sigma r is equal to 0 to n by 2 minus 1, x of 2r omega n power 2rk plus sigma r is equal to 0 to n by 2 minus 1, x of 2r plus 1 into omega n power k, omega n power 2rk. In this case, k is equal to 0, 1, so on n minus n by n minus 1. Okay. See, what is omega n power nk? Omega n power nk is equal to e to the power of minus j 2 pi nk by capital N. So what is omega n power 2rk? It should be e to the power of minus j 2 pi into 2rk by capital N, right? We can write it as e to the power of minus j 2 pi into rk by capital N divided by 2. So if we want to represent it in terms of Freddy factor, omega n by 2 power rk, right? So omega n power 2 rk can be represented as omega n by 2 power rk. So this can be further simplified as omega r is equal to 0 to n by 2 minus 1, x of 2r into omega n by 2 power rk plus sigma r is equal to 0 to n by 2 minus 1, x of 2r plus 1 into omega n power k into omega n by 2 power rk. K is equal to 0, 1, so on n minus 1. Is it clear up to here? Okay, fine. And this is up to today's class. Refer class lo idu okasari malla discuss chesi, then I will proceed with all the views. Okay. That's the end of today's class, and you can leave the class now. Thanks for attending.